Dear students, in this final module of this paper, which is organic spectroscopy, we shall study some more combined problems on the various spectroscopic techniques that you have studied in this paper, that is UV, IR, 1H NMR, 13C NMR and mass spectroscopy. After studying this module, you shall be able to solve the problems related with the various spectral techniques that you have learned. You should be able to correlate the given spectra with some outcomes, and then you can make and come to the conclusion that what is the structure of the given compound. And you shall be able to interpret the spectroscopic data given to you. So, before moving to the problems, we have studied some problems in the previous modules also, but we shall continue this in this module, because then after going through these problems, you shall be more confident in solving similar problems. The knowledge and concept of UV visible, IR, 1H NMR, 13C NMR and mass, you have learned that it helps us in solving the problems based on the experimental data. And this will help us in analyzing the experimental data to elucidate the structure of any given organic compound. While analyzing the data of any given particular compound, you must keep some points always in mind, which I have told you earlier also, but let me repeat. In the UV visible spectroscopy, the types of bonds and electrons, they play a very important role, and they help us in understanding the electronic transition. The UV visible spectroscopy hence will give you information regarding the presence of conjugation, carbonyl group, etc. Talking about the IR spectroscopy, the IR values given to you, they will give you information regarding the functional group which is present in that particular compound. Talking about the 1H NMR or the proton magnetic resonance spectroscopy, that will give you the number and environment of the neighboring hydrogen which are present in that particular compound. Talking about the 13C NMR spectra, that will give you information about the different type of carbon atoms which are present in the molecule. And if you are given the mass spectra, the mass spectral data will give you information about the total mass and fragmentation pattern of the molecule, and all these information, by combining them, you can find the structure of any given molecule or compound. So, let us begin with solving some more problems. The question is, if you see these structures as shown to you here, out of these, which will have the highest carbonyl stretching frequency? And you can see here these molecules, they are given here. One is the CH3COCl, one is FCOCl, another is NH2CO CH3, the next one is ClCOCH3, the next one is ClCOOCH3, and the next one is FCOCH3. So, if we look at these, except acetamide, the inductive effect is dominant and the highest carbonyl stretching frequency out of these will be shown by B, that is FCOCl, because in this molecule it involves the largest net inductive effect, which is the withdrawing effect from the carbonyl group. So, hence this molecule B, which is FCOCl, will be showing you the highest carbonyl stretching frequency. Now, let us move to the next question, and the question is, the proton decoupled spectrum of a tribromo benzene consists of two signals only. Now, which particular tribromo benzene it is? So, let us see how to solve this question. If we look at the possible tribromo benzenes, these are the three possible tribromo benzenes as you can see. That is, you can have 1,2,3 tribromo benzene, or you can have 1,2,4 tribromo benzene, or you can have 1,3,5 tribromo benzene. The presence of two signals as given in the question indicate that only two different types of carbon atoms are present in this particular compound. And if we analyze these three possibilities, out of these only 135 tribromobenzene has a degree of symmetry such that it would give only two signals, and therefore the structure which is being looked up in this particular question, it is 135 tribromobenzene. Let us move to the next question now. The question is, predict the structure of the compound whose peaks in the mass spectrum they have M by E values 57 with 100% abundance, 41, 29 and 27. Let us find the answer for this particular question. The predicted structure of this compound will be as shown here. It is tertiary butanol, and in this tertiary butanol you will be getting all these M by E values as given in the question. Moving to the next question. A compound with molecular weight 116 gave the general information as you can see here. In UV spectral data, there is a band at 283 mu and with epsilon value of 22. In IR spectra, is a 3000 to 2500. There is a broad band, then 1715. There is a sharp, and then 13142 centimeter inverse. There is another band. Talking about the NMR spectra, you are given the peaks at these particular values, that is 7.88, there is a singlet for 3 hydrogens, 7.40, there is a triplet for 2 hydrogen, 7.75, there is a triplet for 2 hydrogen, and minus 1.1, there is a singlet for 1 hydrogen. So, based on this, the question is find the structural formula of the compound. In the UV spectrum, the absorption at 283 mu will of low intensity, it indicates the presence of a carbonyl group. So, that is the information we can derive. The presence of carbonyl group is further confirmed by a strong band at 1715 centimeter inverse in the IR and a very broad band at 3000 to 2500 centimeter inverse is characteristics of carboxylic acids. The OH stretching, and it appears as a result of strong hydrogen bonding, as you are aware. The presence of an acid group, that is COH, is also shown by the NMR values, which gives a signal of the singlet at the negative tau value. Thus, the compound under investigation, as far as the information that we have derived, is it contains the carbonyl group as well as a COOH group. Further, two triplets in case of NMR at 7.40 and 7.75, they have the same integral area, and it must be due to the CH2, and clearly there are two methylene groups which must be under different environments, and thus they couple to give rise to two triplets. The appearance of a 3 proton singlet at 7.88 tau must be a methyl group attached with a carbonyl group. Hence, compiling all this information, the compound under investigation is as shown here. It is CH3CO, CH2, CH2, COH. So, you can see here there is a carbonyl group, there is a COH group as we have derived, and there is a CH3 and 2 methylene groups. Coming to the next question. An organic compound forms a molecular ion peak in its mass spectrum at M by E 114. The other prominent peaks which appear at M by E of 85, 72, 57, 41 and 29. You have to name the compound. Out of these peaks value, you can see that the possible structure of the compound will be this one, where you have the phenyl ring joined to CH2, then OCO, CH3, and this all cleavage will justify the peaks values as given in the mass spectrum value. Let us move to the next question now. The compound which is unknown, which you have to identify, has the molecular formula C5H7NO2, and you are given with the IR 1H NMR and 13C NMR spectra. Let us see these spectra one by one carefully. Shown here is the IR spectra. You can notice the band appearing at 1747 centimeter inverse. Then now you are being shown this NMR spectra. Notice there is a quartet and triplet and these peaks available here, and then shown now is the 13C spectra, where you are given these particular peaks for the carbons. Let us try to interpret this data and find out the structure of the unknown organic compound. The molecular formula C5H7NO2. First of all, we will calculate the index of hydrogen deficiency, which is found out to be 3. A quick glance at the IR spectrum, as you can see here, it reveals the source of unsaturation as implied by an index of 3. There is a nitrile group at 2260 centimeter inverse, and this is giving you unsaturation index of 2. And you can also notice there is a carbonyl group peak at 1747 centimeter inverse, and this is also giving you unsaturation index of 1. So, compiling both of these, you will get the unsaturation index of 3. The frequency of the carbonyl absorption indicates it is an unconjugated ester. The appearance of several strong CO bands near 1200 centimeter inverse, as you can see here, they confirm the presence of an ester functional group. We can rule out CC triple bond because they usually absorb at a value of 2150 centimeter inverse, and they have a weaker intensity than the compounds which contain C triple bond N bond. Furthermore, look at the 13C NMR spectra as shown here. The 13C NMR spectra is showing you 5 peaks, and thus it is consistent with the molecular formula which contains 5 carbon atoms. Notice that the carbon atom in the C triple bond N group has a characteristic value, and it is appearing at 113 ppm. In addition, the carbon atom in the ester carbonyl will appear at 163 ppm, and one of the remaining carbon atoms at 63 ppm probably lies next to an electronegative oxygen atom. The remaining 2 carbon atoms which absorb at 25 and 14 ppm, as you can see in the spectra, they are attributed to the remaining methylene and methyl carbons. And hence, compiling all this information, the probable structure of this compound will be as shown here. There is a cyano group further joined to methylene, then joined to the ester functionality, and then you have a CH2 and CH3. The 1H NMR spectra shows a classic ethyl pattern, that is a quartet for 2 hydrogens at 4.3 ppm and a triplet for 3 hydrogens at 1.3 ppm. The quartet is strongly influenced by the electronegative oxygen atom, which shifts its downfield, and there is a 2 proton singlet at 3.5 ppm, as you can see in this NMR spectra. So, all this information is again confirming that the structure of the compound is as shown here, that is a cyano joined to CH2, then joined to ester, and then CH2, CH3. Let us move to the next question. Here this is a numerical question, and you have to calculate the chemical shift in ppm, that is parts per million, for a proton that has a resonance of 128 Hz downfield from TMS on a spectrometer which operates at 60 megahertz. Let us try to understand how we can calculate this. This can be calculated from this formula, as you can see here, that is ppm is given to be value of resonance frequency in hertz divided by the value of frequency that instrument operates on. Now, substituting these values, we will be putting here the value of resonance frequency in hertz, which is 128, divided by the value of frequency of instrument, that is 60 megahertz, and 128 divided by 60, we get 2.1 ppm as the value. So, after studying and understanding all these problems that we have discussed in this module and in the previous modules, and prior to that all the spectroscopic techniques, I am very sure that now you can yourself find out the structure of any given compound based on the various spectra information. You can analyze the spectra, find out the values, and collect all these information and get to know what is the structure of the compound. So, dear students, let us now summarize what we have learned in this module. In this particular module, we have studied some questions or problems, and based on that you have now got a understanding on finding out the structure if you are given some spectral data. But before you analyze this spectra, you should always keep some points in mind. A UV visible spectra will give you information regarding the presence of conjugation, especially the carbonyl group, whether it is conjugated, unconjugated, and so on. From the IR spectra will give you information regarding what functional groups are present in the molecule. The 1H NMR will tell you the number and environment of the neighboring hydrogens which are present in that particular molecule. The 13C NMR will give you information about the type of carbon atoms which are present in that particular compound, and the mass spectra will give you the information about the total mass of the compound, as well as when you are fragmenting, then the fragmentation pattern from where it can fragment and what different peaks you get, that all you can derive. So, by combining all this information, one can easily find the structure of the molecule.